Hello guys, Ert here, and I'm back for another math video. And this time I'm presenting a new number system that I've created that has summing rules instead of multiplication rules. Well, okay, there are multiplication rules, but those depend on how you want to use them. So like for this, for this object, right now this is just the base objects. There's multiple different multiplication systems you can do with this, depends on what application you want. I won't be covering those in this video, only the summing rules. Unless the summing rule depends specifically on a multiplication rule, like in the case of the two symbols on the right. So, hang on. Let's start with the first one, the tell. So, the way you want to look at this is, let's do a sum over k, xk, tell n, marking the end of sum using my SUN notation, SUK, oops. And I am definitely making that smaller. That's better. Oh, too small. No, it's perfect actually. That is SUK actually. And then that equals tell n minus 1 sum xk SUK, like that. So basically, and we've got to make sure this is infinite size. So basically the idea is, if you just sum up two things on their own, like say, well no, let's do tell n plus tell n over 2, that just stays tell n. So 3 tell n over 2. But if we continue adding more and more and more elements, let me erase this, we will then get an infinite sum that will go to 1. So tell n over 4, that's a finite sum, so it still returns the tell n branch. And the more terms you sum up, the closer and closer this sum would get to the real axis. So over 8 and then n over 16. I think I drew that right. Yeah, I did. And again, so this sum is still finite. But if we keep adding on elements infinitely, we will just get a real number. So let's visualize this real quick. Oh wait, well, we'll get the branch below the tell n, I'm sorry. And for this, I will set tell -1 equal to 1. So the idea for this is, let's draw a chart real quick. And actually, I don't think I want a full line there. We have the real axis there. And then that is the first, that's tell 0. Then tell 1. And then tell 2. Now, before I go on, I know that 0 convention might seem a little odd there. I'm basing that convention off of set theory with the omega. So like omega naught being the first ordinal. So with all this, let's say we have a term, well, no, like here. We want to add terms one by one. So let's say like that and that. Then let's add another term, still on the tell 0 axis. Well, right now it's between tell 0 and 1, but we'll just call this entire gap tell 0. There's that, and then if we keep summing up terms infinitely, this will approach the real axis, or the real line, I guess, because in this case we're not really using axes. And then obviously the space between tell 0 and tell 1 is tell 1, and in general the space between a tell and its successive tell, or the tell with the index right above it, will be the tell with the upper index. And of course, again, using tell 1 to tell 0, start at tell 1, and we start summing values, and it eventually approaches the tell 0 axis. And then tell 2 to tell 1, same idea, so on and so forth. Now, the interesting idea for this, or, well, the application I see this being used for, outside of what I'm going to be using it for in future videos, is a separate version of 1. So let's say we wanted to do e to the x plus, no, I'm not going to go with x instead. Let me do 2 plus 3 tell 0 plus 5 tell 1, and so on. Now, obviously, you'd want to come up with a multiplication system for this. And for simplicity, we'll just set tell m times tell n to 0 for this example, assuming m is not equal to n. And if m is equal to n, then we just get tell n back, or tell m, which in this case would be equal. So that's the multiplication system we're going to go with for now. And basically this with this multiplication system would just be 1 plus, let's do a sum. And for this I'll do x0, x1, and so on. And actually that should be e squared from this 2. And then after that, we can do e to the xn minus 1, tell n, and that is n greater than or equal to 0, and obviously the SU notation. So there's the formula for that using this multiplication system. And as you can see, it just acts as a parallel. This minus 1 is minus a function at 0. So, yeah, let's just think of arcsine, I guess. If we wanted to do arcsine with this, oh no, that's also, arcsine is 0, so it equals 0. Never mind. Arccosine, yeah, that would work. Arccosine at 0 is pi over 2. So at 0 equals pi over 2. So this formula would just be, let's see, the arccosine of the real part plus the sum over n our cosine of, what is it, of xn minus pi over 2, if we were to do this system. And this a just resembles a 2, by the way. I should mention that. Yeah, and then times tel n, that n. There we go, Suen. So editor here, I made a lot of mistakes in that last clip, and I commented them as much as possible. But I thought I'd clear something up there. So that let me write. So that e to the xn minus 1. In the formula, I believe that was, let's see, it was sum over n of e to the xn minus 1, su n, and then there's e to the x 0 there, which x to 0 was the 2 in that example. X sub 0 is already included, so that's a. In this case, the a is just equal to 2. So that actually was not the correct formula. If you didn't see the comment that I had written, it was actually supposed to be e to the a plus the sum over n. Oh, and that was supposed to have a tail there. Sum over n, e, not x, e to the xn plus a minus e to the a, tel n sum n, or su n. And the full formula for that specific multiplication system, which I've worked with many times, would be the function of a plus sum xn tel n is just equal to f of a plus the sum of f of a plus x sub n, well, sum over n, minus f of a. What can I write? There we go. Then times tel n. So that's the correct formula for that. And while I'm not going to prove it in this video, it's very easy for you to prove just using Taylor series. And for the arc cosine example, that would have been arc cosine of 2 plus a big sum, of which, if I was paying attention to the fact that I was using arc cosine, I would have known that that wasn't the best function to use, because the arc cosine of 2 is not defined in the real numbers, only in the complex numbers. And in fact, the same thing occurs for, like, I think all of my examples in this video. So yeah, just ignore the fact that arc cosine 2 is complex. That was my mistake, but at least I realized what I was doing when I was editing. Okay, that's it for now. Now for the next part, which would be for Vocalic L. Okay, so now for the Vocalic L unit, or as I'm going to be calling it, Votel. So Votel is based on a power rule instead of a subscript or subnet rule, as I call it. So the idea here is the sum, as n goes from r to infinity, of x sub n Votel n equals, okay, well, I need to do the Sue. Sue n equals Votel r minus 1, I'm sorry, not n. R minus 1 times the sum of x sub n. Sum of x sub n. There we go. And I don't need the indices, but I'll do that anyways. So there's that formula. And now what this resembles, let me write this down real quick, is basically, it kind of resembles 1/2 in a way. So we usually would have the geometric sum 1/2 to the n, and I think that'd be, n equals 1 to infinity. So that, Sue n equals 1. That's the standard. Or if you want to write it out like this, 1/2 plus 1/4 plus 1/8 plus 1/16 plus so on equals 1. Now, if we multiply both sides by 1/2, we just get 1/4 plus 1/8 plus 1/16 plus so on equals 1/2. And we can continue going on with this. So if we do like 1/8 plus 1/16, like that, plus dot, 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 that equals 1/4. Now, from what I've seen, I believe this is the only geometric sum with this sort of property. However, I might be wrong about that. I'm not sure. But the idea is, instead of doing the 1/2, we're just doing Votel. So Votel. Actually, let me do a different visualization for this. So again, we have the real axis, and I'm going to do this. So we have Votel 1. So Votel 1. Then this will be Votel 2. Then Votel cubed. Then Votel to the 4th, to the 5th, and so on till you get to 1. Or the other way you can put this is Votel to the infinity is 1. Now, that's not an exact formula. That's more like a limit. But this is a very good way to visualize the Votels as an infinite root of 1. So that's a good way to memorize those. And of course, you can do other things with powers and all that. All you have to know is the minimum. So say you had e to the, 2 Votel cubed plus 5 Votel to the 7th. The solution to this would be 1 plus some object times Votel 2, because the minimum is 3, while the minimum Votel exponent is 3, and you're subtracting 1 from that to make 2. And obviously, I could calculate that. Actually, that's very easy. Now that I think about it, I don't know why I didn't just go ahead and do it. I think that'd be e to the 2 plus 5, which would be e to the 7th. minus 1, right? Times Votel squared. And obviously you could do a lot more with that. You can do pretty much any function, and it's actually pretty easy to find values for these functions, compared to if you didn't have the infinite sum rule and you just decided to do something like e to the 2x squared plus x to the 7th. You'd have to do composition of functions and all of that, and that can be pretty nasty sometimes. So this just allows for an easy way to compose these functions, in quotes, without having to fully compose them and at least get the total value out of them. So, well, at least get the total or the summed value out of them. So, next we have, what's the other one? Oh my goodness, I have to go all the way up. Next, we have Bytel. So Bytel sums to 0 instead of 1. And again, we're back to the subnet objects. So the rule for this is just like the original tel until you get to the default index. Let me write this down. There we go. Okay, yeah. Oh wait, and then that needs to be Sue. Sum xn. And then we'll do zero equals 0. And actually, I think that's supposed to be -1. Yeah, -1. So now we have Bytel, and it just sums to 0 as tel sum to 1. And the way we can visualize this is by seeing this as an object smaller than 0, in a sense. So if we do the regular number line, yeah, let me do that, and I'm going to do 0, there's that, negative infinity, positive infinity, so on. And I'm going to do 1 for no reason at all, other than, and -1, just to make it look complete. So now we go down in size, make something smaller than 0, not less than, smaller than, big difference. And for this we get Bytel 1. So Bytel 1, then that is Bytel 2, Bytel 3, 4, and so on. And now we get an infinity root of 0, I guess. Or, in other words, Bytel n to the infinity equals 0. Now, another way you can see this is if you take the infinity root on both sides. I know that's not a legal operation, but we're just rolling with it for now. We get 0 to the 1 over infinity, which is just 0. So, yes, I know this equation looks a little strange, and I know that this 0 to the 0 is supposed to be an indeterminate. But I'm saying we can use bytel as a way to represent 0 to the 0. I'm not saying it's the exact value of 0 to the 0. So, yes, in calculus, we still need the limits. We still need all of that. Bytel is a way to pass over that and pretend like there is a solution to 0 to the 0. So, yes, technically that does mean if we did e to the 0, that would become, that most likely just become bytel 1, I guess, or bytel anything. So, yes, 0 to 0 is still undefined because you can do, hang on, let me make the eraser smaller. Because you can do any bytel and not just bytel 1 or bytel 0. But, of course, you can use the bytels as a better representation for 0 to the 0. Now let's see. The infinite sum part of this. So we have a big object, well, a very small object plus a slightly bigger object than that. Let's just do, I guess, a square root plus a cube root plus a fourth root and so on. If you can visualize it like I'm visualizing it. So, yes, technically, yes, we don't really deal with multiplication rules here, but just like we have omegas past infinity for set theory, we can see these bytels being, I guess, the ordinal for things smaller than 0, in a way. So, I'm not sure how many applications this would have, but I think it would definitely be useful in some way, shape, or form. So next is tritel, which is not the eraser. Don't use the eraser to write. Tritel is the same thing, but with powers. And just like the votel unit, we get this formula. Hang on, let me write it down. What is it? N equals. And then we get this formula. And of course, there's more to this because by the tritel to the 0 is equal to 0 in a sense. I'm not saying it is because obviously anything to 0 is 1. Well, anything finite. In this case, that equation might actually make sense because this is an infinitesimal that is either smaller than 0 or, who knows, it might just be a different representation of 0 that can use powers. So, in a sense, that formula could make sense, but usually we would probably just use tritel to the 0 equals 1 for convention. this is just meant to represent the sum rule. So like the sum of xn, try tell n from n is greater than or equal to 1 would just be 0 no matter what the xn's are. And then if we went past that, so if we did, and actually let me go and write this down. So x1 try tell plus x2 try tell squared plus so on, we get 0. But then if we just go from 2, n greater than or equal to 2, xn try tell to the n, we get try tell to the first power. You don't really need to write the 1 because it's probably assumed, but I'm doing it anyways. Try tell to the first power times the sum of all the xn's. So that's pretty much what we're dealing with, just infinite sums. So now to finish off the video, as a summary, we get the sum of, wait, hang on. The sum xn, that n, well, tell n equals, well, with the su, sorry, equals just the sum of xn, and I should probably do 1. And that can, oh wait, no, that's 0, I'm sorry. For this, yeah, that's 0. Equals sum xn. And then we get the bytel, which just, oh, oops. The bytel, which just goes to 0. And then you can do the same thing with in relation to powers. So that to the n, and is greater than or equal to 1, I should say. That, yeah, that equals the sum over xn. And then the try tell n is just, it just goes to 0. So that's basically the summary for this video. And next video we'll be talking about different empty products and how to make sense of formulas based on the idea that x is 0 does not equal 1. So thank you for watching, thanks for joining, and I will see you in the next one. Bye!